All right, in this video, we're going to talk about the extra sum of squares regression and the reduced sum of squares residual. So what's the basic idea here? Okay, basic idea is we have data on some variable y. Okay, and then we also have data on some predictor variables, say x1, x2, etc. Okay, and what we want to think about is, we could build a model with only x1, right? So like I could build a model that has, the simple linear regression model, and all I have is x1, I plus epsilon sub I. Okay, this is my simple linear regression model. I could have this model, okay, or I could have a model that also has x2, all right, adding in another predictor variable, or I could have another model that also has x3, right, etc. Right? But of course, there's got to be a price that you pay. Otherwise, everyone would just always have however many predictors they have. They would just go ahead and put them in, try to predict y. Okay? Yes, of course, there is a price that you pay for adding in additional predictors. Okay? And so the idea behind extra sums of squares regression and reduced sums of squares residual is to basically figure out, was it worth it? Right? Did x2 help enough that it was worth it to include x2 in the model? Did x2 improve my model significantly? Okay? To improve the fit of this model. Right? So I'm gonna notation-wise, I'm gonna call this first model model 1. Okay? And it has the parameter beta 1. And we are going to assume that we're always going to use that intercept. Of course, not all models have intercepts, right? So notation-wise, I'm going to clarify that I am using a model with an intercept, and I'm going to clarify that by using this given, I have the intercept. Okay. The second model is going to be a model with the parameters beta 2 and beta 1, and I do have the intercept. So given the intercept is there. Okay, so for both these models, I'm trying to figure out which model should I use? Should I include x2 or not, right? That's a basic question I'm thinking of right now. For both of these models, I could calculate my sum of squares, right? So sum of squares total, notation-wise, sometimes you'll see this written as SST, same thing. Okay, so sums of squares total equals the sum of squares regression, okay, same thing as SSR, plus the sum of squares residual, right? Notation-wise, your textbook might use SSE. Personally, I'm not a fan of this notation because R is both in residual and regression, so students often get confused with it. But I just want to point this out that you can have either notation. Okay, so so this is we've shown this before that the sums of squares you can partition them like this, right? And let's just remember, what is sums of squares total? It's the difference between the observed y and the mean of the y's squared. All right, so you take those differences, you square them, then you sum them all up. Okay, sum of squares regression is the difference between the predicted y minus the mean squared, plus the regression is the sum of all the residuals squared. Okay. So for each of these models, we can partition our sums of squares, right? For model 1 and model 2. Now, starting with sums of squares total, let's think about this. yi minus y bar, right? So our observed value of y minus the mean of y. Does this care about which model you use? Does it care about the x values that you're using? Not at all. You can calculate sum of squares total 100% just by giving me what the y is. I don't care about x at all. So sum of squares total, it stays the same regardless of the model. That is a very key point. Okay, so you want to make sure you make sense of that. So sums of squares total, it's going to stay the same regardless of the model because it's the difference between y, each y value, and the mean of the y values. Doesn't depend on x at all. All right. Next, I'm going to skip regression and move on to residuals because I think it's easier to think about residuals. Okay. So the residuals. Let's think about this as we go from model 1 to model 2. So model 1 has x1 trying to predict y. Model 2 still has x1 trying to predict y. Okay? So whatever residual you found here in model 1, so the difference between your predicted and the observed, you'd have a similar residual here, except, but now you have another variable, right? Another variable that's trying to help. So this additional variable could potentially reduce that residual, right? In no possible way could this residual for model 2 be more than the residual for model 1 because x1 is in both the models. So x2 can either help or do nothing for us. If it does nothing for us, then the residuals for both models will be the same. If it helps, then the residuals from model 2 will be less. Okay, so that is a very key, important point. Let me write it down. So this guy, SS residual, it decreases, okay, or stays the same, right? If x2 did nothing to help me, or stays the same with additional model parameters. Let me scroll down a little bit. Okay. So as you continue to add on model parameters, right, as long as you're not deleting some of the parameters that were in it before, then this has got to decrease. All right. The amount that it decreases is called the reduced sum of squares residual. Okay. So the amount that SS residual decreases is the reduced sum of squares residual. All right. Okay. So now let's move on to SS regression. Now, if this guy stays the same and this guy decreases, and I know when I take the sum, right, I get the guy on the left, then this must be increasing. And it makes sense because basically what we're doing when we're creating a prediction is we're getting further and further away than just like the basic using just y bar to estimate y, right? We're trying to do better and better than just y bar. So sum of squares regression is going to increase. Okay, or stay the same. In this situation where x2 did nothing to help me, then it'll just stay the same. So, or stay the same with additional model parameters. Okay, and the amount that it increases, so the amount that SS regression increases is the extra sum of squares regression. Okay? All right, so how do I write this notation-wise? Okay, how do I do this calculation using the proper notation? All right, starting with extra sum of squares regression. Let's write that down. Extra sum of squares regression when we add that second model. What did we add? We added in beta 2 to the model, right? When we add beta 2, right? Which is equivalently the same thing as saying we added x2, right? When we add beta 2 to a model already containing beta 1, equivalently x1, and beta naught. All right, so basically, what is the extra sum of squares regression? When we start with a model, the simple linear regression model, and then we add on this additional model parameter x2. All right, notation-wise, the way we would write this is we would say, okay, we want to find the sum of squares regression for this new parameter beta 2, given that beta 1 and beta naught were already in the model. Okay, this is going to equal the sum of squares regression for that big model, right? For the second model, the model with both beta 2 and beta 1, right? Minus the sum of squares regression for the small model. Right? Basically, the amount that sum of squares regression increased is the difference between the sum of squares regression for the big model minus the sum of squares regression for the small model. Okay? And I just want to point out before I move on to talking about the reduced sum of squares residual is this notation. This is my favorite notation because really what we're doing is we're adding in model parameters, right? Betas. Now, not everyone uses this notation, and I've seen it written probably 50-50 in different textbooks where they'll use the x's, right? I'm not a big fan of that because x2 could actually just be x1 squared, right? What you're doing is you're adding in new model parameters, but the x values are not necessarily unique from each other, right? You can have a more complicated model by just adding in, maybe square terms or interaction terms, etc. Nevertheless, you could potentially see this written. I just want to show you what the different notation would be. If you have x, this would be written as SSR or SS regression for x2 given x1. So you see how it's just beta is now x. And then they don't have the intercept. So that's another reason I don't like this notation because it's not clear about whether or not this model has an intercept. Not all models have intercepts. Nevertheless, like I said, you'll see it like this. So I just want to show you the different notation. So sum of squares regression or SSR, and this will be x2, x1. Okay, so this is a model that has both x2 and x1, just like it had both beta 2 and beta 1. All right, minus sum of squares regression for the model that only has x1, just like this one only has beta 1. Same thing. Okay. Okay. What about reduced sum of squares residual? When we add beta 2, which is the same thing as adding x2, right, to a model already containing beta 1 and beta naught. Okay, so basically, how much did the sum of squares regression get reduced when we added in that new model parameter x2? Okay, how do I write this notation-wise? We would write this as SS residual, right? Exactly the same, right? For this new beta 2, given that the model already has beta 1 and beta naught. Right, and different textbooks will write this as SSE for x2 given x1. Same thing. Okay, this is going to equal, right, So it's the amount that you decrease. So remember, which model has the bigger residual? The bigger residual is going to come from the smaller model. So this would be SS residual for your small model minus SS residual for the bigger model. The bigger model should have the smaller residuals. So beta 2, beta 1, given beta naught. Okay. Right, and notation-wise, of course, this is the same as SSE of, instead of beta, some people will write that just as x1, and then they don't say anything about the intercept. And then they'll say this is SSE for x2, x1, for the model with both x1 and x2.